This mic is also on for some reason.
ये था एक
सेकंड, ये क्लिकर से नहीं चल रहा.
इससे कनेक्टेड है ना. विदाउट दिस चल रहा है क्या क्लिपर या वो भी नहीं चल रहा?
Without this one,
मतलब ये प्रोजेक्टर डिस्कनेक्ट कर दे तो.
प्रोजेक्टर भी HDMI इसमें लगा.
हाँ नहीं मतलब ये डिस्कनेक्ट करके ट्राई करते हैं कि क्लिपर चल रहा है लैपटॉप में.
नहीं, वो USB चाहिए ना इसका रिसीवर.
अच्छा
ठीक.
आ गया.
हाँ, and a very weird one. Low battery. There's low battery.
दूसरा देख लेते हैं. I think this is nice. This has full battery.
How does it turn off? Hold. Low battery.
एक्चुअली नीचे यहाँ पे फुल दिखा रहा है. ये फुल दिखा रहा है.
Okay. Is it on?
And it turn on. No, sir.
Hello everyone. Can you hear me fine? Hello. Can you hear me fine in the back? All right. As you might know, Dan is not here, so I'll be teaching today's and next lecture, which are on neural networks. How many of you know what neural networks are? Come on. That's it? You've heard of neural networks? All right. You've used neural networks? Do you use phones? You have. Let's see. Anyway, we've been looking at, or you guys have been looking at trying to learn classifiers to separate out data which have different labels. So here an example of data on a single dimension with red and blue labels. And this is not linearly separable, right? Okay. So what can you do if you want to make a classifier to classify such data? Anybody? You can transform the feature space, all right. Good solution. Any other solution? There's a solution on the slide. you're not, yeah, sorry.
You can try using a more expressive class of functions and all linear later.
Right, so you can try to use a more expressive class of functions than a linear classifier, right? So as our friend told us, you can try to blow up the feature space into something where you can actually learn a linear classifier to separate the data, but there might be issues with it. Can anyone try to tell us what those issues might be? Issues in trying to separate data or blow up a feature space so that they're linearly separable? Yes?
It might not be obvious how you should blow up feature space.
Precisely. So you don't know how you want to blow up the feature space to so that the data is now linearly separable. So there are these two schools of thoughts. We don't still know what the clear answer is, but neural networks try to take the first approach, where you try to learn a more expressive classifier than a linear classifier. Okay, so on a very high level, neural networks are these kind of multi-layer networks which are composed of very simple classifiers. They are composed in a specific architecture, which we'll go over. But for example, you've seen the linear threshold unit multiple times in this course. So for example, you can take one of those linear threshold units and compose them in parallel, and then you can stack them up and try to make these more expressive function approximators. So this, for example, is one of those. So these are also called multi-layer perceptrons. So you can, the single linear threshold unit is also known as perceptron, and when you stack them up in multiple layers, they're also called multi-layer perceptrons. Quick piece of history. So how it all started was these two researchers in 1943 showed us that we can use these single linear threshold units to model very simple Boolean functions. So for example, and, you could do that between two Boolean variables if you have, say, a weight value of 1 and a threshold which is 1.5 times that. Is it clear how you're able to model an AND function using that? Can anybody try to quickly run us through that? Come on. Anybody? Yes?
Only if both of them are on, that will become 2, and then if you subtract 1.5 from that, it will still be positive. But if only one of them are on or none of them are on, it will always be negative.
Precisely. Everybody follow that? Right? And similarly, you could do that for OR, where your threshold value is now lower than the weight value. So if any one of them are on, they will be on, but if both of them are off, you will have a negative 0.5, which will be false. Right? Similarly, not is very simple. But suppose you have a Boolean function XOR with its data in 2 dimensions shown there. Could you use a linear classifier or a linear threshold unit to model this Boolean function? And no, right? Because you won't be able to find a single plane so that you can separate the solid circles with the transparent ones, the hollow ones. Okay, so somebody, I don't remember the name, showed in the 1950s that if you stack up 2 linear threshold units in this manner, in this 2-layered 2-unit network, you're able to model XORs now. Can anybody try to give an intuition of why this would work? If you can see it? Of why just now using 3 linear threshold units. So there are 3 linear threshold units, right? You take one from I1, I2 into H3, one from I1, I2 into H4, and then H3 and H4 to this O5. So these 3 linear threshold units, and how is this making our life easy? Okay.
So one of the person, what one perceptron does is it basically makes a line and divides the plane into 2 parts, 2 labels basically. Now when you have 2 perceptrons, they basically divide the plane into 4 different parts, and you can compose those labels somehow to make something which is non-linear itself.
Not precisely, but yes, the intuition is correct. So you can imagine the first 2 linear thresholds making 2 hyperplanes. So imagine one is right below the 2 solid circles, and it says everything on the top right is of one label. So now you're misclassifying that lone hollow point on the top right corner. But imagine another linear classifier, which is on the right side of these two solid circles, and saying everything on the bottom left half is of the other class. So now you only have this band which says that, oh, this is one class and everything apart from that band is of the other. Is that clear? At least you get the intuition that you're now trying to compose linear classifiers or these hyperplanes, trying to intersect them into making more expressive functions. Right? Yes?
But what you just explained doesn't address the hidden layer or what it does?
I don't see the word hidden layer here. Don't rush ahead. There are just these two classifiers. So I1, I2, and H3 from one linear threshold unit. Is that clear?
Oh, I got you. I thought you were saying I1 was one of them, I2 was the other one, and then the H is just...
Sorry, I1 and I2 are the two inputs. There are your X, the input space.
Okay, got it.
Okay, great. All right, so coming back. So what this is trying to show you is how you're using one linear threshold. So the inputs are all these blue circles, and then you have one blue circle on top, which is the output of this linear threshold unit. And you have three of them in parallel, and then you have a linear threshold unit which takes three inputs, which are also called the hidden inputs because they are not the actual output of the model, to output one single variable, right? So is this clear? Okay, so just as a working thesis for this class, that the idea is to stack up multiple of these linear threshold units into this architecture and try to come up with more expressive functions. So what you will learn in these two lectures is basically why, or get an intuition of why this is possible, and how do you also make effective learning methods to learn this. So you might have a way to express any arbitrary complex function, but if you're not able to learn it, then it's useless. So we'll try to see how you can do it, and also we'll look at applications of it in the real world, but that will be most of the next lecture. So in this one, you will try to see how you try to learn these multi-layer networks. Okay, just to give a formal definition, these are functions from the X space to the Y space. In its working definition, there is nothing different from a linear threshold unit, right? They also took some input X and they output a value Y. Only that how you model these functions is different now. Just to look at exactly what is going on inside them. So you have the two linear threshold units first, which output values H3 and H4, right? And then you have the values H3 and H4, which are now acting as inputs to this third linear threshold unit, which outputs O5. So just in the last equation, if you were to plug in the values of H3 and H4, you can now see how it is a more complex function than you were working on with before, right? Okay, so because we will try to learn these functions, we should know what are the parameters that we're actually trying to learn when we're trying to learn these multi-layer networks. Can anybody tell us what those parameters are in this case? All right, if you had a single linear threshold unit, forget everything else in the slide, just look at the nodes I1, I2, and H3. Is that a single linear threshold? Or resounding yes? Okay. What are the parameters for those? What are the parameters for a single linear threshold unit? The weight vectors and the threshold value, right? So what are those in this case, for example, for one of the linear threshold units? The T1, for example, written over there on the left. All right, so that's correct. W13, W14, and T1, right? In the first equation, you can see those are the parameters. So what are the parameters for this whole two-layered, two-hidden network that we're looking at?
All of your W's and all of your T's.
Right, all of your W's and all of your T's. So now we actually have 6 weight vectors and 3 threshold units to learn. So just from intuition, so you could also have made a single linear threshold unit with 2 inputs and 1 output, and your only parameters there would be, or how many parameters would you have in that case? 2 plus 1, right? 2 weight vectors and 1 threshold unit, and now you have 9 instead of those. So this is just trying to give you the intuition that things have become a little more difficult. Now you're trying to learn 9 parameter values instead of 3, right? Okay. All right. And in the majority of this lecture, what we'll be looking at is the back propagation algorithm, which is this learning algorithm to learn such multi-layer networks. What is the one learning algorithm you've seen throughout this class until now, or maybe recently? Yes, but a particular instantiation of it. Sorry? Perceptron. So perceptron was a learning algorithm for the linear threshold units you looked at, but they cannot be generalized to these multi-layer networks. But as you guys said, gradient descent, which is a more general algorithm, is still not clear how to use it directly for these multi-layer networks, but we'll see how backpropagation algorithm actually gives us a way to do it. Okay. Quick bit of motivation. So how it all started was people were trying to come up with models. Actually, psychologists were trying to come up with models of the human brain, and we realized we knew that we have neurons that are connected, and there is information as electricity that passes through our bodies, and they were trying to come up with models that mimic the brain. Didn't quite happen, but at least we got neural networks out of those. So they are inspired by biological neural networks, but they're not identical to them. So if anybody tells you that you're mimicking the brain, you're not. Anyway, one other thing that has led to their popularity is parallelism. So we now have architectures, or rather hardwares, such as GPUs and TPUs, you might have heard of them, that are able to train these neural networks in a much faster manner than you would have done on your CPUs. We'll get a very high-level intuition of how parallelism actually helps neural networks. Okay. And okay, on a very high level, do we remember the hidden layer we saw in the previous slides? Those have also been used to get some representation of the data, but let's forget it. We'll look at it in the next lecture. Okay, let's deep dive into the neural network architecture. So we know what the linear threshold unit is. So even though I said this is exactly used in these multi-layer networks, they are not. Can anybody try to come up with a reason of why exactly that threshold unit is not used in multi-layer networks? 2 pieces of hints. Okay, go for it.
Yeah, don't you want to normalize it at each node to be between 0 and 1?
Not really. Why do you think we need to normalize them between 0 and 1?
I've seen implementations where you do that.
You could do it, but there is no necessity to do it.
Okay.
Right. So not really a blocking path. There is something else about these linear threshold units. Can anybody else? Does anybody else have an intuition? It has to do with learning becomes an issue, and the words gradient descent. Yes.
The weights, you can't really keep the bit particularly well. So then when you backwards propagating, you can't really
Yeah, basically the intuition is this is not a differentiable function, right? And why is it not differentiable? It's discontinuous. Where is it discontinuous at? T. The threshold T, right? There's a step where you go from -1 or whatever 0 2 plus 1. So it is discontinuous at that point and not differentiable. And why is differentiation needed? Or why do you want these functions to be differentiable? To calculate the gradient, right? Because we'll be learning using gradient descent in some manner, and you will not be able to do so if you cannot compute the gradient of a function. So what people came out with was we tried to approximate these linear threshold units or this threshold function using a continuous differentiable function, right? So one example of this is the sigmoid or the logistic function, which is for a given input x, it is modeled as 1 over 1 plus e to the negative x. All right? And it looks like that. Let's try to see what happens to this function. So when x is 0, can anybody try to work out what the value is, or just allowed? Yeah, so basically, yeah, it's half because e to the negative 0 is 1 and 1 over 2 is half. So it kind of is in the middle ground where you had a discontinuity in a linear threshold unit. You now have a value of 0.5. A linear threshold unit at the value when x is arbitrarily large is, sorry, 1, the linear threshold unit. Even this would be approaching 1 when x gets very large, because e to the negative very large value will be close to 0. 1 over 1 plus something very close to 0 would be approaching 1, right? All right. For arbitrarily negatively large value, sorry, 0. E to the negative something very large would be e to the something very large in positive values. So 1 over that value would be approaching 0. Right? Okay, great. So this is some kind of a, but, okay, yes.
I wanted to ask if you're applying this function to every step, like to each layer, or just at the very end?
At each step. We'll look at that. But did everybody get the question? So the question was, are we using this function only at the output or at every step? And the answer is at every step. So here, okay, how many linear threshold units do we have in this network? Sorry? 5, right? So 3 on that hidden layer, and then 2 at the top. So instead of using the sign function, or this hard threshold function on these 5 linear threshold units, you will instead be using this logistic function now. So it is everywhere. Yes?
When we were doing previous algorithms, we basically got around the non-differentiability by saying we're only going to update if it's an incorrect observation.
Yes.
Could you explain why we can't apply some similar logic to this situation?
That's a very, very good point. So the question is, precisely in the perceptron algorithm, what we were doing was we would only update our weight vectors or our trainable parameters when we made an error. So actually, that was not a way to get around the non-differentiability, because even if you correctly classified a point, you could still have updated the value. So those are two different things. But so this is not really a solution for it. And also, you don't know what the update rule is for in this case. So we will be able to analytically compute what the update rule is. We will do that in this class, but that needs the functions to be differentiable. One quick question before I get to you. So the linear threshold unit is non-differentiable at the threshold value, but what is the gradient apart from that? Sorry? 0, right? It's a flat function. So it won't even work anywhere else. So the perceptron algorithm just worked because they actually were computing the gradient of a linear function rather than a flat function. All right. You had a question.
I just wanted to clarify that the x in this case is actually wx minus t.
Yes, we will, yeah. Precisely. So so we'll be using this value net j throughout the lecture. So let's look at that. It is just this summation of, or the linear function of your weight vectors with the inputs are. And then the output of a single neuron or that single circle cell that we've been looking at is this logistic function now over it. So 1 over 1 plus e to the negative something, and that something is net j minus tj. Is that clear, everyone? If you have any doubts, clarifications you want at this point, you should, because we'll be building upon this throughout the lecture. Or you could go to sleep. Either of those work. Okay. A quick note on kind of the things we've been talking about in this lecture. So it has been shown that any Boolean function on this planet can be represented by two-layer neural networks. A second piece of point. Any bounded continuous function can be approximated by a two-layer network. These are very powerful results that were shown and that led to the popularity of neural networks. Because you now don't have to come up with these kernel functions based on the data and blowing up spaces. You know that if I have a two-layer neural network, and if somebody gives me a learning algorithm, I will be able to mimic any bounded continuous function. There is a bit of a catch there. You don't know the size of the neural network. You don't know how many linear threshold units you will have to compose, or how many, basically in this case, how many linear thresholds you would want, but it is possible. Right, and the last point is also very important. Any function, it can be discontinuous as well, can be approximated by a three-layer neural network. So this is also called the universality theorem, and this actually kind of changed the game, the proof. Don't really, I think these are just the things you need to care about of why we actually try to research neural networks or try to use them. Anyway, okay. How do we make predictions using neural networks? Yes?
In the last slide, you cannot, for the last fourth point, you cannot really simulate non-continuous functions using the sigmoid. I mean, you need discrete.
Yes, as in when you know that you want discrete outputs, you will have to discretize them out, but they do work in general. All right. If I were to give you a neural network, I were to tell you its weights, I were to give you a single point x, how would you make predictions from it?
So in this case, it looks like you have 5 output buckets. Whichever one is the highest value, I assume you would assign to be the winner, and you would say that that's your output?
Sorry, no. So, okay, we're not doing multi-class classification. So, okay, we don't have a single output value that we're looking for. We're not looking for a scalar value. I should have made this clear. You can also have a vector of 5 as an output. Is that clear? Right? Sorry, yes.
So do you just calculate the output of each layer in parallel and then just apply?
Yes, I'll get to it in a minute. So just to make one thing clear, we're not looking at functions that produce a scalar value. These values can be vectors as well. In this case, for example, your input is a vector of size 2, right? I've reversed the inputs and outputs in this figure for some reason. And the arrow also points in the wrong direction. Anyway, there are inputs of size 2, and the output is a vector of size 5. So we're not looking for voting or anything. You'll just get a real valued vector of size 5. All right. And you were correct. So how you would make predictions in this case is you will be given this vector of size 2. You will compute these linear threshold values or the sigmoid function values for H1 layer, right? You would take those two values and compute 4 sigmoid function values at the H2 layer. Then you would take that H2, H4, and then the output, right? So this is also a reason why these networks are called feed-forward networks. You might have heard that term, because you're computing values at a layer and then feeding them forward to the next layer. You do some computations and again feed them forward to the next layer. And that is also where the term deep learning comes from is when you have tens or hundreds of these layers, you're increasing the depth of the network, and hence the term deep learning. All right. What is required to fully specify a neural network? Anybody? Yes.
The geometry, weights, and thesis.
Yes, which is also known as the architecture, this one. So the architecture which tells you that there are 3 hidden layers. The first hidden layer is 2 units, the next one is 4, and the one after that is 4. You would usually know the output space is 5, and all the weight values and the biases for these linear functions that are computing. Okay, great. Can you think of a reason why neural network predictions can be quicker than you going over each of them serially, try to compute them? Or can you think of a way to make computations fast in what you've looked at? Yes, but how?
Split up each layer to work on.
You would need to split up layers anyhow, because you would need all the computation from the previous layer to do any computation on the next layer. So that part is not parallelizable. There is something else that you can parallelize here to make these computations fast. Yes?
Every node in a single layer, you should be able to parallelize.
Precisely, correct. So if you look at the H1 layer, for example, which has 2 output values that you need to compute, the left one only depends on its inputs, and the right one also only depends on its inputs. So they can be made parallel. You can do these computations in parallel because they don't depend on each other. So on a single layer, you can parallelize computations. And then once you get those outputs, then you start with the computation of the next layer. But this has also led to them being very popular and them being fast, even though they look like they cannot be made fast. What makes them nonlinear approximators? Anybody? Does anybody know why they are nonlinear functions or nonlinear approximators?
Doesn't it just relate to the fact that since we have several layers, we're like, we can do interactions between linear separators rather than just one linear separator?
Not really. So the answer we got was because we're using multiple layers, these interactions would lead to non-linearity in our functions. So that is not true. I don't have a proof for that, but you could, if you have a linear function and you compose it in another linear function, the output is a linear function. So that is one of the properties of linear functions, that linear functions, when composed, lead to linear functions. So that is not the reason. But there is something you do when you compute this linear function, so the value net j that we computed. After that, you do something that induces nonlinearity. Sorry? Right, so the logistic function that we looked at, the sigmoid function, this one is a nonlinear function, right? It is not a straight line. That is where this nonlinearity comes from. And that is the main reason why neural networks work. Okay. All right, we'll look at how do we train neural networks. Okay, just a quick recap. This is what we had for a 2-layer, 2-node neural network. So you're computing the hidden values, then you compute some output value, you have some trainable parameters. And now we're looking at how can we learn, for example, in this case, these 9 values, given some input and output data. Okay. And we all know gradient descent. Can somebody give us a quick intuition of what gradient descent is? Or when would you want to use gradient descent? Anybody? Okay.
When you want to find the local minimum or maximum of a function, you can use gradient descent because the gradient of a function basically tells you that if you move in this sort of direction, your value of the function will basically increase. If you want to minimize it, you can move in the opposite direction, and if you want to maximize it, you can carry forward in the direction.
Right. Yeah, I'll just model your words up. And so we're given a function. In this case, for example, this ERR, the error function, which is a function of some parameters. In this case, the parameters are the weight values that you looked at, that you want to learn. Now, for any given values of these weights, you will have a value of this error function. And in all of or most of machine learning, what you do is you try to come up with this function that if you minimize, you will achieve your goal of whatever task you were trying to solve. So we try to minimize this error function. Now, gradient descent tells you that the quickest way to minimize this function is to move in the negative, in the direction of the negative gradient. So for example, if you start out, so this is a function which only takes one parameter, or this is a single scalar value, and suppose you start out with this value w0, which is for which the error function is quite high. You can do better. So you would compute the gradient of this function, which points in the top right corner, because if you move w0 slightly to the right, you will actually increase the value of the function, but you try to move in the negative direction of that because you want to minimize this function. All right, so you reach at this point w1. And similarly, you would compute the gradient there, and you will make these small stochastic steps, right? Okay, so this is the founding algorithm that will be used for learning these neural networks. So just a quick note on what is one possible error function. So this is an error function which takes in for any data point d. Okay, first of all, you have k outputs in this case, right? So for any data point, you will get k truth values, which are written as t sub k and d, where and then you compute some output, which is o, k, and d. What this error function does is, let's look at the first summation. It computes the distance, the scalar distance between the truth and the output, takes the square of that, and then sums it over all different outputs. That is the loss or the error for one data point, and then sums it over all data points in your data set. Does anybody know the name of this error function? It is quite widely used and hence named. This is the least squares, yes. Yeah. The mean would have come in if instead of half, there would have been a 1 over d. But yes, least squares is this function. So you're trying to minimize the square of the distance between your predicted and the output value. Okay, so on a very high level, what you would want to do is compute the gradient of this error function e with respect to all weight values wij in your network, and then try to push them in the negative direction of this gradient. And the R is a learning rate that you've seen also in the perceptron algorithm, right? Yes?
Would you mind going back one slide quickly?
Sorry?
Would you mind going back one slide? Yeah, just let me ask a dumb question here.
No question that dumb. Yes, go for it.
Oh, just wait. What happens? What stops us from just taking the derivative of the error function, setting it to 0, and then immediately knowing what our minimum is?
That's not a dumb question at all, first of all. Does anybody know the answer for that? If everybody knows it, then it's a dumb question, probably. But I'm sure. Does anybody have a solution for that? So the argument is, or the idea is, that you get the error function, you take the gradient of it, and you set it to 0. And then whatever weight values you get, or you know when it gets to 0.
Is it because that the way that we are doing it leads to like an algorithmic approach to learning rather than I don't see how you would sort of use
No, forget what we're doing now. Imagine it's the 1950s. You came out with this neural network and you're now trying to devise ways to learn it. And your friend tells you that, oh, I will just set it to 0 and then try to find out what the weight values are that leads to this 0. Um, why didn't people do that? Not really. You would not be even able to do it. Yes?
Since it's a non-convex function, it's difficult to do that analytically. So algorithmically, we're still doing the same. We want the gradient to go to 0.
Mm-hmm.
But if you want to do it analytically, it needs to be convex function for you to be able to do it easily.
Yes, but there is something even more fundamental of an issue with trying to do it.
There might be a minimum.
No, even if there was a single minima. So you have one equation with multiple parameters. You would not be able to analytically find the values that would lead to that value, right? So you might have learned in your linear analysis class that if you're given a system of 2 linear equations, or if you're given a system of linear equations with, say, 2 variables, you need at least 2 equations to be able to solve them, right? So here you're trying to solve for multiple variables using just one equation. Not possible. So you have to resolve to these step-based analytical methods to be able to do it. All right? Not a dumb question. Anyway, so the approach that people take is you try to find the gradient of this function with respect to all possible weight values, and then you try to move in the negative of that weight value, or of the gradient value. Right? Is that high-level intuition clear? The only issue with this is how do you even compute the gradient of this very complex multi-layer network? We'll see how to do that, and that is precisely the back propagation algorithm. Don't need this. All right. Anyway, let's try to see how we can find the gradient of that error function we just defined. Before that, imagine this is a function from y to z. Okay, so y is an input, z is the output. That arrow represents a function. So for any given value of y, you would be able to compute the value of z, right? For example, z could be 2y squared. And you would also be able to compute the derivative of z with respect to y, right? What would that be in this case? 4y. That tells you that if you increase y, z would also increase. The sign of that would tell you that. All right, great. Now, some compositions. So if z is a function of y, and y is a function of x, then z is also a function of x, right? Okay, great. The derivative in that case becomes this. So you have a function, you have a value x, you have a function, you have a value y, which is a function of x, dependent on x, and then you have a value z, which depends on y. So the gradient of z with respect to x is actually the gradient of z with respect to y times the gradient of y with respect to z. Have you guys seen this in math courses before? Anyway, otherwise you'll have to take my word for it. Okay, so can you now kind of see what is happening? So your multi-layer networks are precisely these chained computations, right? So you were given an input, you computed some hidden value, and then from that hidden value, you computed some other hidden value or the output. And we want to find the gradient with respect to all weight values in the network. So you might need things like these or tricks like these in your bag. Great. So we will use these facts in the back propagation algorithm to find optimal weight values. So what would be happening is, for example, in this case, your z could be the error function. For example, the least squares function we looked at. And then we would need to know how to differentiate that error function with respect to all possible weight values not only at the top layer, but everywhere else in the network as well, and and then do gradient descent over that. Okay. One possibly last composition is if z is a function of x, but there are multiple ways to reach that, right? There are multiple paths to reach that. So here y1 and y2 are functions of x, and then z is a function of y1 and y2. This also would look similar to what we had before. So you have an input x, say a single input x, then you have a hidden layer of multiple units, and then you have a single output z, right? So there are multiple paths you need to go through to find the value of z. In that case, the gradients for individual paths add up. So these parallel paths lead to addition of gradients, and we know how to compute the gradients of individual paths. Those are just the derivatives, or those are just the multiplications of gradients on the path. So similarly, you can have that for when there are multiple paths to reach z. Any questions at this point? None at all? Okay. All right, so we know what we're after. We'll use gradient descent to change these weights, right? Sorry, yes.
Sorry, real quick.
Mhm.
When you're looking at all these sort of stacked differentiable functions, you're looking at loss function at kind of the end, and then sort of beyond your last set of nodes, you're looking at your loss function, and then intermediately you're calculating the gradient from these sigmoid functions.
Yes, yes. So just a clarification note. Yes, there is this, say, stacked neural network. You are given inputs, you go through these multi-layered computations, and you get some output at the end. Now, given some truth values in your data set, you compute an error function at the end. That is the only feedback you're getting, right? So yes, so these are usually called feedbacks or signals. So these are the only signals you're getting, or the only signal you're getting at the end, and only based on this, now you update all weight values, and that is what we'll try to see how to do that, right? So we'll use gradient descent. So we'll try to first compute the gradient of this error function with respect to all weights, and then we'll try to move in the negative direction of that. Okay. We'll be using chain rule because we have changed computations. And we'll also look at how this idea of memoization from dynamic programming that you must have already seen also helps us in backpropagation. Not very important now, just these 2 points of we're using gradient descent, and we'll have to use chain rule somehow to find gradients. So we'll go over this backpropagation algorithm in depth, but if you don't follow that, it's not the most important thing. But do remember these 2 points, that you're using chain rule and you're doing gradient descent at the end of the day. All right, great. On a very high level, there are 2 steps now in training. You have the forward step that does what? Compute the output. So you're going in the forward direction given an input, go through these multi-layer computations, and compute the output. And then we introduce this backward step where you first compute the gradients of this error function, and then you update the weights. And why is this called the backward step is what we'll look at now, because of how these computations actually roll out. But just again, a forward step which helps you compute outputs, and then there'll be some backward step in which you'll be making updates to the weights. So just to draw analogies, this is very similar to what we were doing in a perceptron, in the perceptron algorithm, right? You were doing this step of forward computation where you computed the value, and then if you made an error, you were updating the values according to the perceptron rule. That is something like the backward step. Okay, great. I don't think we need a quiz, you guys are good. Okay. Right, just quick note. Somebody has something important. All right. What's more important than neural networks? All right, so this is the function we looked at. Just a quick note. Remember this sigmoid function, 1 over 1 plus e to the negative x. That is the nonlinear function, or also called the activation function, that we'll be using in our neural networks. Sorry? Okay. And then computations and forward. Okay, let's look at what happens at the topmost layer. Okay, so we have these output nodes 1 through k, and we are looking at one of these hidden nodes, j, and and let's look at one of these output nodes, say oi. So the weight value corresponding to the connection between them is called, say, wij. Is this clear? So we have a hidden node j in the penultimate layer, which connects to this output node oi, and this weight value is ij, and we'll look at how or what the gradient of the error function is with respect to this. This is very similar to just finding the gradient of a linear threshold unit, right? That if you forget everything that has happened in the past, what you have is just a linear threshold unit with this nonlinear activation function, but things should look very similar. Anyway, so you have this value oi, right? Which depends on this neuron j because of this function. Remember this?
It also depends on t.
Yes, but t is a parameter. So the note was it also depends on t, and yes, but I'm talking about the inputs. So it obviously depends on also the w's and the t's, which are the parameters, and the actual value that you output j, which is dependent on the weights. But yes, the parameters are still w's and the t's. Okay, so this is the sigmoid function, which depends on this value net j, which depends on the weight vector, or the weight value wij. All right. So what we'll be using is this chain rule that we looked at before. So we know that the error function depends on the O's, right? It was the least squares function. We know that the O's depends on this value net j, right? And the net j's depend on these weight values. Is this clear? Mm-hmm.
Is t true, like the true result? And in case of the error function, like the lowercase t, does it stand for like the actual?
Yes. So the tk in the least squares function on the top is the gold truth that you've been given. So suppose you were doing some kind of a binary classification, it would be either 0 or 1. Okay. Is this clear? Okay, so we now know that to compute the gradient of this weight value ij in a top layer, what we need to find in turn is 3 gradient values, and then multiply them. Okay, let's look at the first gradient value. Okay, so that is gradient of ed with respect to oj, or okay, or oi. Wow. What would it be? It would look something like this. Is this clear? Probably quite straightforward, right? Okay. Let's look at the other function that we wanted to look at. Was the gradient of oj with respect to net j, where that tells you what this is, the sigmoid function. So what we now have to do is compute. Oh, sorry. We're first looking at, the last term over here. The net j by wj, which is net j equals just a linear sum of the inputs with respect to wij. So what is the gradient of net j with respect to wij? Anybody? Sorry? xi, right? Because it doesn't depend on any of the other inputs or weights in that sum. Right. And the last one is you're looking for the gradient of this function. It's quite simple to compute. You don't have to exactly do it, but this is the value. All right? So we now have these three gradient values, which is negative ti minus oi. Okay? Then you have a value xi for the other function, and then you have oi times 1 minus oi. All right? So if you were to now, again, look at this gradient that we were after, we now have all the components needed to find that gradient, which is this. So we found out the gradient of the error function with respect to oj is tj minus oj. So it depends on whatever the truth value is and what you computed. And that is all it should depend on, right? Okay. The next one is what is the output or what is the gradient of this output you computed with respect to whatever computations you did in this node j, right? Okay, you have that. And then the value that you computed in this node j, the value net j, depends on whatever the weight value is, and also obviously the input. And we're trying to see, and we saw that the gradient for that is xi. So we now have these three computations, and we know that the gradient is whatever this. I'm writing this again here, and what you would actually be doing is multiplying this with a learning rate of r, and you would update the values ij. Okay. I have made this subscript or this variable delta j to denote this particular value. You don't have to remember it, but we'll see why I'm doing this in a while. Anyway, any questions at this point? Okay. All right. Things will get a little involved, but you should hopefully be able to get a high-level intuition of what is happening. So what we did previously was compute the gradient of any weight value in the topmost layer, which was kind of very straightforward. Now what we're trying to do is compute the gradient at any of the intermediate layers. So let's say the layer before that. And why is that tricky? Right, exactly. So that is a little more involved because this wij affects the value that you produce at this jth node in the figure, right? And then that affects all the output values now, all from 1 through k. So now you would have to look at gradients or the changes. So basically, if you change wij in any of the intermediate nodes, you're now affecting all values. So you have to take all of them into account when you're computing the gradient. Is that clear? Does anybody have a question? Yeah? Somebody who doesn't think that is the case? Okay. Okay, so this does look like the multipath example we looked at before. So just in general, what would be happening? Can anybody try to give us a very high-level intuition of what might we be doing now? So, okay, so what is the result we saw when we saw that there are multiple paths to reach a value z, for example, from x? Yes?
We sum up all the chains.
Right, so we sum up the gradients from all the chains. So that is something that we'll be looking at again. Exactly. So let's look at the gradient of the error function with respect to wij, but where this wij is now from one of the hidden layers. So let's say just the penultimate layer. Okay, so this is precisely the gradient of the error function with respect to net j, and then the gradient of net j with respect to wij. Okay, a very simple chain rule, right? Okay. We already know what the gradient of net j with respect to wij is. It's xi, right? Straightforward. And now what we want to find out is the gradient of this ed with respect to the jth value, right? So does that little clique look like the slide we saw before, where you have a single input, you have multiple paths, and then you reach a single output? So the z there corresponds to ed over here, the x here, x there is the jth node here, and some multiple paths. Okay. So that is precisely the sum of gradients over all these independent paths. And what is the gradient of one of the paths? Say, let's say that goes through the output node k, is the gradient of the error function with respect to that node k, one of the intermediate nodes, and the output, and the gradient of net k with respect to net j. Does it look fine? Any questions? Yes.
It'd be easy to follow if we had a layer height number in the index.
Okay. Next year. If I don't graduate. Anyway, so but this looks fine. So you're taking the gradient of one of the paths that starts at this node j, goes through the output node k, and then leads to the error function, and then we are summing over this gradient over all paths. Okay. So this term, the one I've written delta k, is something that we've actually already computed in the previous slide. Let's show you. So that was the gradient ed, the gradient of ed with respect to net j, and we call this term delta j. This is exactly what we get now. And is it now clear why I said that memoization helps in back propagation? Can anybody try to tell us why or what are we memorizing? Okay.
That case for every node.
Is for, yes. So delta k.
As we move ahead, we can use them directly because it's a chain rule of differentiation.
Yes. So basically what we're looking at when you're computing the gradient at an intermediate layer, you're actually using some computations you did in the previous layer. So you don't have to do them again. So is it now becoming a little clear why it is called the back propagation algorithm? Can anybody try to justify the name? Yes?
So basically what we're doing is we're going down the path, and at each layer, what we're doing is we're computing the gradient of the error function with respect to the nets of the nodes of that layer.
Mm-hmm.
Then we basically store those and use those in the next layer by we're substituting the delta.
Right. So the answer, which is correct, is you're actually first computing the gradients at the topmost layer, right? Which is actually the last layer you used when you were doing the forward computation. And then you start in reverse, you compute the gradients there, you store them, you make some updates, and then you use those values, and then you will have to use those values when you're finding the gradients at some other layer. Then you'll have to store those values, and then those will be used in the layer below that. So this signal that you get from the top as error function now propagates down these layers in a reverse manner. So hence the name back propagation. Okay. Okay. This is quite straightforward now after this. Now what we have to find is the derivative of net k with respect to net j. These are details, you don't have to really worry about them, but again, you'll have to use some kind of a chain rule where you find first the derivative of net k with respect to the output value, which is with the activation function, the sigmoid, and then whatever the gradient of that value is with respect to whatever the input it got, the net j, which is without the activation function, just the linear function that you had computed. And we had done these computations before, so we know what these values are. Anyway, but now, just looking at this equation, you see that you are, when you're trying to compute the gradient of this error function with respect to the weight value, you're summing over the paths it affects, and you're summing over those gradients in this equation. Okay. Okay, and you'll have to again store that huge value as some variable delta in that node, and that will again be used in a layer below that. So this is kind of what happens in the back propagation algorithm, and it has been shown that it works very well. It has some nice properties, as we saw, that you're able to use memorization, which makes it fast. You can also parallelize computations, as you did in the forward pass. In a single layer, you're also able to do them here, because of which you're able to kind of use the architectural advancements that are made in the community to help us train these networks. Okay. Does anybody want to go over this algorithm for us? Anybody? Like, what is the high-level picture of what is happening? All right, I'll do it for you. You get some inputs, and you have some truth values associated to them, right? You initialize your network with some weight values. For example, with some noise, you can also start with all values being 0, but that is shown not to really help. So for example, you draw a random number from a uniform random generator, right? And you initialize all these weight values. So when you looked at the two-node network, there were 9 values that you will have to initialize, right? There were the 6 weight parameters and the 3 threshold parameters. And then what you do is you take one of the data points from your data, you do the forward pass, compute the O values, the output values, compute the gradients using the backpropagation algorithm, and make an update to the weight values. And you keep doing this until whatever your stopping criteria is. You reach some accuracy values, you decrease the loss to a certain value, or some other things. Okay, and the same algorithm works for more hidden layers. Okay, when does this class end?
20. Sorry, 50.
10:50, right? All right. So let's try to. You're able to see this, right? Okay. All right. So here we have some data in orange and blue. Is this linearly separable? Yes. So if I just use x1 and x2 as my inputs and use a single layer, which amounts to using a single linear threshold unit, will we be able to separate this? Yes, right? It is linearly separable. So very quickly you see it learns a function on the right with some test loss which is very, very low, and is able to separate this data using just a single neuron, right? Does this make sense? All right. All right, let's try to look at this data in which you have the blues and the oranges in some kind of a concentric circle space. Is this data linearly separable? No. Okay, so you will not be able to separate this using a linear classifier. Let's try to verify that. It is struggling. Yeah, we knew that. Okay, if I now use 2 linear functions, or not really linear, but 2 hidden neurons in between, will we be able to separate this data now? Sorry? How many people think yes? 1, 2, 3. How many people say no? What do the others think? You don't know. Yeah, even they don't know. But Okay, why do you think you will not be able to separate this?
I think it will basically just draw two lines, and I cannot think of a way of drawing two lines and separating this.
Yes, that is kind of the correct intuition. So if you remember XOR, the function XOR that we were looking at, we were able to separate that because we had these two linear functions and you were able to make a band out of those, or you could make a full area after you intersect them. But you will probably not be able to do it when you try to do it using these two hidden layers. So what is happening in this case? So this hidden network, so I'm hovering over this hidden neuron at the top in between, is learning this linear classifier, which says everything on the top is orange, everything below that is blue. This one is learning the other linear function, and then they're kind of intersecting them and making this shape, right? So not separable using two hidden networks. But can we do it using 3 neurons now?
You can introduce a new layer.
Yes, we could do that. But suppose you only have a single layer. No, right? But can we do it using 3 hidden neurons now? Should be able to do it, right? Because if we suppose make a line right at the left side of that blue, we should be able to form some kind of a triangle and be able to do it. Oh, sorry. Right? And this is what you look at. So you see one of the nodes making a plane, the other one tries to cut it from the bottom, the other one from the top right, and the intersection of them forms this triangle now, and is able to solve this data or classify this data correctly. Great. Okay, let's look at something much more challenging. So it has this weird spiral that starts out with orange here, and then something in between which is blue. Can we do this with 3? No, right? No way. Yes. No way. All right, let me see something that actually. Oops. Let's make this. All right. What do you think might happen? Doesn't really work in this case. But okay, you might see me restart this again and again, and you will see different outputs every time. Can somebody try to tell us what might be happening?
Random initialization.
Yes, can you expand on that?
Basically, since the
Whoa, yeah, go for it.
Since the surface of this function is not exactly convex, that sort of thing, so if you start at different sort of points, you have a better chance of reaching a better point. Because you'll only be reaching local minima, there's no...
You don't know if you'll reach better points, but the high level intuition is that what you're actually doing is this stochastic gradient descent, where you're starting at a point, and then you're making these local steps, right? So depending on where you start in this error function, you might reach different places. So which is also called this idea of random initialization. So you start by randomly initializing your network with different weights and seeing what happens. So we see that it kind of does it, right? Training it more doesn't really help. But in around 1,000 epochs, one epoch is going over all your training data one time. So when it saw the training data, say around 1,000 times, it was able to learn this with this very complex network of 2 hidden layers and 8 units. All right, but in the beginning of this class, somebody gave us the idea of trying to blow up the feature space, right? So you can also still combine these two ideas. You can blow up the feature space, right? So I introduced these 2 new features, x1 squared and x2 squared, and still use complex classifiers, which are not linear functions, and see what happens. So let's see. So, right. So it reached the same amount of test loss, 0.02, but much faster. Right? So in around 300 iterations, was it able to do this? So this kind of still tells you that even though neural networks are very powerful, they're still not just enough. Because you can imagine that some of these hidden neurons are trying to mimic the x1 squared function and the x2 squared function. It takes time for it to learn that, oh yes, this is a useful path that I have to go down, and this might actually help. But if you already give it something that helps it classify easily, then it might learn with less training iterations. Is this kind of clear or helping you understand what is going on? Yes.
Do more nodes in the network necessarily yield a higher quality just at the expense of higher computation time?
What do you think? So the question is, do more hidden neurons always lead to a better classifier at the expense of training time? Let's get your thoughts first on this.
I think that higher computation time is almost certainly true.
Mm-hmm.
I'm just wondering if that's the only drawback. I could imagine both scenarios in which maybe adding more just adds sort of complication that's necessary.
Mm-hmm.
I could also imagine that any superfluous nodes would kind of end up just with weights of zero, so it doesn't matter.
Let's go with that. So basically it's a gray solution. Is that he thinks that you will probably add complications, and it is not very clear that you will always see gains, and that is precisely correct. So adding more hidden neurons does mean that you're giving your model more expressive power, but you're also complicating the learning process, right? By adding more parameters to your data. We saw that when we moved from this single hidden layer, single hidden node, which is just a simple linear threshold unit, you had 3 parameters you needed to train. But when you move to a 2-layer, 2 hidden network, you now have 9 parameters. So they add up in a multiplicative order, right? So you are actually complicating the training process, and it is not very clear. And it is actually when you get some data, you have to try to find a good sweet spot where your learning is good and you're seeing good accuracies and low training times. Yes.
By doing that, adding more neurons and then giving the model more expressivity, aren't you also possibly going to overfit?
Yes. So overfit. I think it's okay. Okay. Yes. Can anybody tell us what is the idea of overfitting? We have a couple of minutes left. Okay. Yes.
When you just make your model very, very expressive, stuff starts fitting the training data very specifically, so sometimes it can end up fitting noise or things like that.
Exactly. So in all of machine learning, what we're after is generalization. Is we're given a sample of the problem that we're after, and you're trying to learn a model that will be able to work always. But because you're only sampling a few data points from the universe, you might end up trying to model noise or some other quirks that might have gotten introduced. So that is the whole idea of overfitting. And yes, everybody wants to avoid overfitting. And yes, if you try to add more neurons and try to make your neural network very expressive, it might lead to actually overfitting, that when you start modeling noise and quirks in the training data, which might end up hurting your performance in the test set. Okay. Right. Since we'll be out of time in a minute, actually I can introduce you the idea of dropout. Okay. Very quickly, I'll probably go over this again. So this is the idea proposed in 2012. Is one of the ways to avoid overfitting and has been proved to be very helpful. And the idea is, what you do is when you're looking at, say, a single data point to make updates, you don't use all of the network. You remove some nodes from it and don't use them and still try to make predictions from it. It is not very clear why this helps, but there has been some intuitions and theories going around. And the most convincing ones is that imagine one of the weight values is getting very large, and the model very heavily starts depending on one of the nodes, and this might actually hurt your model. So what you do is you remove certain nodes and you try to evenly distribute computational power across your network so that none of the weight values get very large and starts very heavily influencing the decisions that the model makes. So on a very high level, that is the idea that it does. This is one of the plots from their paper where when they were not using dropout, you see this very classic overfitting curve where your classification error goes down, but then it starts going up. But when they started using dropout, they saw that they were able to train the network much better. One other quick note on neural networks, that there is no guarantee of convergence with neural networks because these are highly non-convex functions, very expressive. The algorithm that we use, backpropagation, is an approximate algorithm that just kind of works, but there is no guarantee. Whereas in perceptron, you saw that if your data is consistent, there is a strict guarantee of convergence, right? Okay. I will leave you with this. All right. Hi.
A quick question. Can we
Sure.
go further?
Yes,
can
go
we
for it.
Go back. We actually in a.
No, Nitish.
I'm sorry?
Yeah, go for it.
Yeah, when is your PA? I had some doubts, so I'm going to ask you in person.
Me?
Yeah.
I am not a TA for the course, so I don't have TA hours.
Can I have an appointment?
What questions? You have questions regarding this lecture? Can you try to post them on Piazza and see if people don't answer them?
But then is it possible to have an appointment with you in person?
Thanks.
Possibly, if your questions don't get answered over Piazza, is there a specific reason you don't want to use Piazza?
Yeah, I don't want to. I want to learn it like. I mean, since you know the subject really well, I thought of asking you.
No, even the TAs know it very well.
I
They are
really
TAs.
doubt it. That's right. Because there have been previous issues in which they never knew what happens, and I had to ask the professor.
Okay. You can try to email the professor in that case.
Okay.
If it doesn't get solved, you can try to email me.
Okay.
Yes. But I would heavily suggest you first try to go to the resources in the course. You have the TAs, you have the recitation class, you have
Are you an instructor in this course? Or
no,
not
I'm
at all?
nobody.
Right.
The instructor has office hours, right?
Yeah, yeah.
Dan Roth has his
yeah,
office
yeah.
hours, so you can try to pose your questions in,
Okay.
in those spaces.
Yeah, sure.
I'm very sure you will get all your answers
Yeah.
there. Otherwise, you can obviously email me, but I'm sure you will get answers. Yes.
Yeah. Why are you like plotting these two together?
Why are we doing that? So there is a very simple, quick proof that you can do. I can try to do it for you.
But yeah, I understand the chain rule, but like these are like different functions, right?
Yes.
But they're totally irrelevant. Are they kind of irrelevant to each other, or these? So like why are plotting these two together? Because I like so the.
They are not.
So the derivative with z to respect to x, I understand like so it's like z to the y1 and y1 to x, and the other approach like z to y2 and y2 to the x. But why are you plotting these two together?
Because the final value of z depends on both of them, right? So if you slightly change x, so what does this mean?
Yeah, it's the. I'm sorry, it's the derivative, partial derivative of z with respect to x.
Yes, but what does that mean?
It means like how the if x changes, what will you expect to influence the z?
Exactly. And if x changes, then in this what will change? both y1 and y2.
So the both y1 and y2 will change. And
Yes.
the y1 and y2 will have influence to the z, so
Exactly.
So we're plugging
So
them.
when not that doesn't tell you that you have to plus them together.
So
That just tells you that
we need to
they will
contain
both.
both of them.
Yes, that tells you that both of them will appear in the gradient,
Uh-huh.
but how will they appear? You don't know.
So
They might have been multiplied together.
so
They might have
yeah,
been some other function.
times or other
Any function on this
Okay.
planet. But
but these two terms will appear in the final function.
exactly. So you get to know that, and then why do they actually get added up? Is a very simple. So, that's true. If you have a function y, which is x plus x squared, what is the gradient of y with respect to x?
It's 1 plus 2x.
You did add up, right? So that is kind of exactly what is happening. So z, in that case, is actually y1 plus y2. So when you take the derivative of z with, say, respect to y1, what would it be?
It will be 1.
1. And similarly with respect to
This will be
it's also equal to 1. But now imagine y1 was actually equal to, say, 2x, or what do we use? X, right? So let's not use x because the gradient becomes 1. Let's use x squared and x cubed. Okay? So suppose y1 is x squared. So what is the gradient of z with respect to, okay, let's try to say that y1 is x1 squared and y2 is x2 squared, is x2 cubed. So what is the derivative of z with respect to x1?
1 times
2x1, right? And the gradient of z with respect to x2? 3x squared. 3x2 squared, right? So the gradient of z with respect to, now suppose x1 was equal to x and x2 was equal to x. So this is the graph I'm taking. I'm saying x goes to x1, goes to x2, equal. And then this goes to z, but which is equal to x1 squared plus x2 cubed. Right? So you found the gradient of with respect to x1 is 2x, 3x squared, and if they're added up, you will find that and because this is 1, right? So we know that the chain rule tells us when they're in path, they get multiplied. So the gradient of this is what? If x is equal to x1, so the gradient of x with respect to x1 is 1. So you do 1 times the x, 1 squared. No, sorry, 2x1. 2x1 plus 1 times 3x2 squared, but x1 and x2 are equal. So it becomes 2x1 plus 3x squared. Right? So you kind of now get the idea of what it is. Okay. Do you know where? Okay, I think.
What? Oh, yeah.
Okay, great. Thanks a lot. Was the lecture fine, helpful?
Yes, it's very thorough.
Sorry?
Very thorough.
All right. Great. Thanks a lot. If you have any suggestions for the next lecture, was I too fast? Was I too slow? Was I asking a lot of questions? Was I not asking a lot of questions?
I personally find the interaction very helpful. It's something that Rob, I think, tends away from, so I like that change of pace. But
Oh, really? Okay. I thought even Dan asks a lot of questions in class. Not?
yeah, that's true. I guess in this case, I
Okay.
definitely felt like a more interactive class.
Okay.
One thing it might make sense to take an extra 5 minutes to go over is maybe just one more time just because it's kind of the whole point and it's quite complicated, is the derivation of the d arrow
actually